So I'd like to talk about the LEO-Augmentation and its impacts on the wide area PPP-RTK positioning and time transfer. So I will first concentrate on the positioning issues and then move to a long baseline time transfer based on the same model. And if time allows, I'd like to talk about the differences between simulations and the real-world situations. So, well, what is wide area PPP-RTK and why do we care about the impacts of LEO-Augmentation on it? So PPP-RTK is a well-known method to achieve ambiguity resolution and provide users with single receiver-based high-precision positioning. Basically, the network part will calculate and provide users with the satellite clocks, satellite phase biases to enable the integer ambiguity resolution, and optionally also the ionospheric information to enable fast integer ambiguity resolution. So in a wide area, extending to like thousands of kilometers with network stations only sparsely distributed on this wide area, it is challenging to precisely interpolate the ionospheric delays. So in such a case, we often opt to the so-called ionosphere-float case, so that users need to deal with the ionospheric delays by themselves. In the so-called undifferenced and uncombined mode, which is used in this study, this means the estimation of the ionospheric delays by the users. And well, eventually the users will achieve ambiguity resolution, but this will require a longer convergence time, and also the convergence time becomes sensitive to the observation model, which means that if you use single or multi-GNSS, if the user status is in kinematic mode or static mode, such things. So that's the reason that we would like to have a look at the impacts of LEO-Augmentation on the wide area PPP-RTK positioning. So here we have selected a network in China extending thousands of kilometers, as we see here. We have all these 22 blue network stations sparsely distributed in this area, and we have 19 user stations. Using these 19 user stations, we have performed like over 1,000 hourly sessions to check the convergence and tested in both the static and kinematic mode in ambiguity fixed and float modes. And using GPS-only scenario and the dual constellation scenarios. And for the LEO-Augmentation, we have used a rather typical constellation consisting of two types of LEO orbits, namely inclined orbits consisting of 120 satellites distributed on 12 orbital planes, and also near polar orbits consisting of 30 satellites distributed on 3 different orbital planes. This is also the plane configuration of sync space. And here we can see that with this LEO-Augmentation, the visible satellite number has been increased to over 30, added of course by the current GNSS broadcasting Air 1 and Air 5 as an example. So what is the influences of this LEO-Augmentation? Here, using these 1,000 hourly sessions, we have 1 sigma percentile line of the horizontal arrows in static mode as an example. Here, the red line and the blue lines illustrates the cases without LEO-Augmentation. We can see that the partial ambiguity resolution, of course, helps with the fast convergence. However, with the LEO-Augmentation, namely the black line and green line, we can see that the fast convergence can be achieved even in ambiguity float mode within like 1 to 2 minutes to 1 decimeter. And also, let's have a look at other cases. Here, the G here means GPS only, and GC means GPS PDS dual constellation scenario. King means the user is in kinematic mode. Stay means the user is in static mode. We can see that no matter if we use single or dual GNSS, no matter if the user is in kinematic or static mode, no matter if we fix or not fixing the ambiguities, with LEO-Augmentation, the fast convergence time can always be achieved within like 2 minutes for convergence to 1 decimeter and like 2 to 3 minutes to convergence to 5 decimeter. Of course, here I have used 30 seconds sampling data. With 1 second sampling data, the convergence could be even faster. So we can see that the major contribution of LEO-Augmentation is not only the fast convergence, but makes the fast convergence insensitive to the GNSS-based observation model. So we all know that in PPP-RTK, atmospheric interpolation is always a bottleneck, no matter including the ionospheric interpolation and tropospheric interpolation. Here, in all cases, we do not have any atmospheric interpolation, and we can see that this bottleneck might be naturally solved when adding the LEO LEO-Augmentation. So here, let's also have a look at the long baseline time transfer applying the same model, because I'm basically from the national time, so it's interesting to have a look at the time. So here, we are applying actually the same model. The only difference is that now we care more about the clocks instead of the coordinates. In the first step, we can see that the estimable receiver clock at the user side is already the clock difference between the user and the reference network station, plus the difference of IF code bias between the user and the reference network station at the first epoch. So we can see that here we have analytically already solved the problem of the correlation between the time-varying clocks and time-varying code bias, because here this is only the first epoch code bias. So this can be achieved by actually imposing a temporal link on the code bias. And as a second step, we try to form the between station difference between two user receiver clocks. In such a case, we can remove a certain kind of the systematic effects brought by the network products. And if one of the user receiver is said to be a time lab connected with a high performance atomic clocks, then the actual user, namely the second user, could be synchronized to this time lab. And also, the third step, we can form a weighted average of the solutions for each GNSS, because the estimable receiver clock, as we see here, is actually constellation dependent because of this bias. And this constant is of less concern. So after forming this weighted average, the nature is not changed. It's still the receiver clock difference plus a constant. It's just stability can be further improved by making this weighted average. So let's have a look at the networks that we have selected for this test. This is the network also extending to 1,000 kilometers in Europe. Here we have used the GPS and Galileo dual frequency observations, and all these network stations are sparsely distributed in this large area, and we have selected PPP connected with high-performance hydrogen laser as a reference network station. And also we have selected 3 user stations all connected with high-performance hydrogen lasers, and in such a way we can form 2 very long baselines, not very long, but long baselines between Onslow and Brooks and Onslow and Wissel, which is nearly 1,000 kilometers. So let's have a look at the results. Here is the first step, namely we directly estimate the PPP-RTK user clock. We can see that the 70 STB is not that optimized, it's still about 0.15 to 0.2 nanoseconds. But after forming the single difference between 2 user stations, most of the common systematic effects can be reduced. And these are the 2 baselines that I mentioned before, namely the 2 baselines between the 3 users. And we can see that the 7-day STD is reduced to like 0.07 to 0.11 nanoseconds, and 1-day STD to like 30 to 70 picoseconds. And when doing the third step, after forming a weighted sum between GPS and Galileo, we can see that the 7-day STD is further improved to like 60 nanoseconds. Here is a modified deviation of the Brooks Onslow baseline of nearly 9,000 kilometers. We can see that in fixed and static mode, the stability is obviously better than in the kinematic mode because of the high correlation between the coordinates and the clocks. But also we can see that here in real-time and filter-based mode, the ambiguity fixing is not necessarily better and not necessarily beneficial for the short-term stability of the clock, because the partial ambiguity resolution could resolve different numbers of ambiguities at different epochs. So these zigzag behaviors might not be that beneficial for the short-term stability of the time transfer. So let's have a look what happened after adding the LEO constellation. The LEO constellation was the same one as I mentioned before, and we can see that in the fixed mode, well, the improvements is not that obvious, but in the static mode, we can already see that the convergence speed has increased by 2 to 3 times. Here we refers to the convergence to 0.5 nanoseconds, and in the kinematic mode, the improvement is rather obvious. The convergence speed is increased by 3 to 5 times. And also we can see that the eventual, the clock residuals becomes a bit lower in the cases without LEO-Augmentation. So these are actually all based on simulations. We already have real LEO navigation signals and provided by different satellite constellations and different providers. I'm working on one, although I'm not authorized to release more information here, but I would like to talk about the differences between simulations and real-world challenges. So in real world, basically, we need to first use the LEO navigation, carrier-based and postoidal range signals properly. This will, of course, relate to a significant upgrade in software and hardware. And also, the LEO satellite-specific systematic biases could be different from those of GNSS satellites in regards to the stability and also the challenges of the fact that there are not a lot of ground stations can receive the downlink LEO navigation signals nowadays. And also, we need to provide users with real-time, high-accuracy LEO satellite orbits and clocks, not in near real-time, not in simulated real-time, but in actual real-time. So I'm actually spending most of the time on this topic, which is not the major topic of this presentation. So I will not go into too much details, but I'm happy for private discussions after the session. So as a summary, we can say that, well, the future LEO-Augmentation will certainly bring benefits to the wide area PPP-RTK, not only about the fast convergence, but also about the fact that the convergence time becomes insensitive to the original GNSS-based model, and the atmospheric interpolation might not be that essential anymore when LEO satellites comes into the current GNSS constellations. Although there are still challenges coming from simulations to the engineering praxis, but I hope when one day the LEO navigation signals are open to the public, all these benefits will come true. Thank you.